Okay, this is one last video about Chapter 10. It's just kind of a collection of a bit of things, and in fact, maybe you can use this as part of your studying for your exam. I'm going to continue on. I'm actually going to talk about nitrogen and phosphorus. That's what this subject is about, and it's in the context of chapter 10. So, again, kind of look, nitrogen and phosphorus are both in group 5. Both 5As, and so therefore we would expect them to have similar properties and actually probably even form similar compounds when you look at some of the common compounds of both. So let's start with nitrogen. We've looked at nitrogen quite a bit, and so one of the things we looked at was nitrogen gas. I'm not going to take time to go through the formal process of determining Lewis structures. I'm just kind of drawing it quickly. But nitrogen gas kind of looks like this. It has a triple bond, and it has each nitrogen has a lone pair. In this case, the formal charge of both nitrogens is 0, and so this is obviously quite stable. I'm going to draw also ammonia, which we've looked at multiple times. Okay. Ammonia again has a formal charge of 0. Also has one lone pair, which makes the shape trigonal pyramidal. Okay, and then I'm also going to look at, I don't think I drew the Lewis structure for this in the previous videos, but I'm going to draw the nitrate ion, which again we've seen a lot when we were doing the earlier chapters. The nitrate anion, that's basically NO3 minus, looks like this. The whole thing, of course, is minus. And each of these oxygens has 3 pairs. And this oxygen has 2 pairs. And you can, in fact, this is an exercise for you to do. I want you to kind of draw the other resonance forms of this and make a comment about how those resonance forms either makes this anion more stable or less stable. Okay, so now, in this situation, this Lewis structure that I've drawn here, you can see that all the octets are fine, but the formal charge of each of these lower oxygens is -1, while the formal charge of the central nitrogen atom is +1. And you add them all up, and that's why you get the minus charge for the anion. In nitrate, in this situation, nitrate, NO3 minus, the nitrogen is in the +5 oxidation state. Okay. So I want to contrast this now with the contrast of the analogous compounds using phosphorus instead of nitrogen. Okay. So first of all, I'll start with the phosphorus analog of ammonia. It's called phosphine, or phosphane is actually the proper name. It actually looks exactly the same when you draw the Lewis structure. Looks like that, and it has the exact same molecular shape as ammonia, which is trigonal pyramidal. Okay. Now, when we talk about the gaseous form, or the elemental form of phosphorus, there is indeed a version of elemental phosphorus gas that looks analogous to nitrogen, but this is far less stable. And I'll show you what the more stable form is in a second, and it's fairly interesting. I'm going to end this video talking about the more stable form of phosphorus. Okay. So, but that does exist. But then the interesting thing, I'm going to erase these now for a second. The interesting bit happens when you look at the phosphate anion, basically as comparing it to the nitrate anion, the analog, and actually looking at some of the other possibilities for phosphorus. So in the phosphate ion, if you remember, actually we did this in the 10th video of chapter 10, essentially looks like this. The whole thing has a 3 negative charge, and if you and again, when you do the formal charge on all of these atoms, you see the formal charge is 0. And then if you think about oxidation number for a moment, the oxidation number for phosphorus in the phosphate anion is +5, just like it was for the nitrogen atom in nitrate. So phosphate and nitrate both have their central atoms in the +5 oxidation state. It's no accident that they end kind of the same, 8. Now, what's interesting though, I think is, and I'm not going to even explain it, I'll leave it as kind of an interesting thing to ponder, is it's a wildly different shape. It has only the phosphate phosphate anion has first of all has a formal charge of 0 as opposed to in nitrate. There's 4 oxygens instead of 3, and of course there's 10 electrons around phosphorus, while of course there's only 8 around nitrogen. Okay, so and I imagine you can already think of reasons because some of the other videos talked about that. Now, what's interesting though is that there's also a phosphite, which is PO3 triple minus, which on the surface looks a little like this. First of all, I forgot to say the shapes of these molecules. The nitrate ion is trigonal planar. Okay, there's no lone pairs. It's one of these AX3 shapes. Okay, and the shape of phosphate is tetrahedral. It's one of these AX4s. Okay, again, no lone pairs in either case. Okay. Now, I want to draw phosphites for a second. Keep this shape in mind, though. We're going to come back to this shape in a second. Phosphite, which is PO3 triple minus, which technically speaking doesn't exist, but it exists in aqueous form, kind of. It's a very strong base, so it actually will suck in a hydrogen, and that the 2 minus variant of this that does exist. But let's just focus on this. It's cleaner to look at. This has, of course, phosphorus in the middle and oxygens around. Okay, and we have essentially okay, and we have a lone pair. All right, so the formal charge of the phosphorus in the middle is 0. You see that? There's 5. There's 1, 2, 3, 4, 5. And the formal charge around each oxygen is -1. Formal charge -1 here, -1 here, -1 here. And that's why the entire anion is a 3 minus. Okay, so in some ways this now, and the oxidation state, if you do the oxidation state of phosphorus here, you'll see that it is +3. Okay, so it's even though it sort of looks analogous to nitrate, the phosphite is actually has the central atom in a different oxidation state, and you can see that the shape is even different. The shape of nitrate is trigonal planar. Let's say AX3, but the shape of phosphite, it's one of these AX3Es. It has a lone pair. So the shape there is trigonal pyramidal. Basically, this lone pair forces these other 3 guys to be, it's sort of tetrahedral-like, but this lone pair squeezes them down, so it's trigonal pyramidal. Okay. All right, so you can see there's some similarities, like when we talk about phosphane and ammonia, but there's definitely some differences if we look at these anions. One last thing, and to finish the thing, I want to look at the kind of dramatic difference in terms of how the elemental form works, at least the gaseous elemental form for phosphorus. Okay, so again, like I mentioned, nitrogen in its elemental form, the most stable, pretty much the only stable form of nitrogen is this. And I mentioned that phosphorus does exist this way also. But the more stable form is actually a form, it's called white phosphorus, or sometimes it's called yellow phosphorus because it's yellow in the light, but it's actually white in the absence of light. It's basically a phosphorus that has 4 atoms. Now, one of the reasons why I thought this would be a good example is that, remember earlier I was saying, you know, in determining Lewis structures, you have to decide what's the central atom. Well, it's kind of interesting when you have a situation where all your atoms are the same, which is the central. We got to pick one of them. So One of the four is your central, and then we're going to put the other three around it. Okay, and then let's do our usual valence check. So phosphorus there's 4 of them, but times 5 each, so we have 20 electrons to deal with. All right, and let's see. Let's put them in. So we'll put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it turns out, and I'm going to go through this quickly rather than struggle on camera, that this isn't actually even really the right shape. And the real shape of white phosphorus, now I'm going to skip all this for a moment, is that each phosphorus is connected to all 3 others. So the phosphorus that I chose as the central atom, it turns out any of the 4 phosphoruses I could have chose as the central atom, because the way they're structured, it's kind of like it's almost like it's a ring. It's a rigid kind of structure where each of the 4 atoms are connected to the other 4, and each of them has a lone pair. So the shape of this, when looking at one of the phosphorus atoms, the shape you would just kind of assume would be AX3E, which is trigonal pyramidal. But is that actually the shape of this molecule? And the answer is nah, not really. It looks more like a box, because each of the phosphoruses are connected to the other. And you can actually search for this on the internet, and you'll see a better 3-dimensional depiction of what it looks like. All right, the last thing that I want to show, boy, I hope I have time for it, is what happens when P4 oxidizes. And it's very flammable, and you can almost kind of tell it's flammable, or it's of high energy, because these extra bonds that kind of make this molecule very rigid, kind of everyone's bonded to each other, makes it very rigid, which is a sign that it's usually a very high energy as well. And sure enough, this, just in the presence of oxygen, will rapidly oxidize, and it forms an interesting compound that I want to draw for you, and that's when I'll end this video. So when P4 mixes with 5 oxygens, it forms a compound called Tetra phosphorus decaoxide. Okay, I want to draw this because it has a really interesting shape, especially as it pertains to phosphate that we've looked at several times. Okay, so I'm going to draw a line here, and I'm going to start with this molecule, and it's not a solid. I mean, this exists as a gas. Looks like this. We have 1 phosphorus up here, and it's double bonded here. And so for the moment, this kind of looks like phosphate. You remember phosphate with its -3 charge. In fact, if I just put brackets on here at 3-, this is phosphate. But the story doesn't end there. This oxygen is connected to the next phosphorus, which has a double bond to O, and it has another oxygen. Okay. This oxygen here is connected to a phosphorus, which has its double O, and it has its own oxygen. And then the last phosphorus down here is actually connected to both of these oxygens. It has its own double O. Yeah. Boy, I always, let's see if I'm going to get this right. Yeah, sorry, this is that one. There you go. Good. So this oxygen connects this P, and then this P has an oxygen also, which happens to be connected over here. Think of this last one as being behind this structure, so it's hard to draw it in three dimensions. But this oxygen's in, this one here is in the front, this one here is in the back, and so this phosphorus on the left has a fourth oxygen, which is also bonded to the phosphorus on the right. That is P4O10. It is also kind of boxy in shape, but it's more stable, which is why this reaction is has quite a negative delta H. So it's more stable, but it's still boxy, which means it's still probably of reasonably high energy. Okay, and if you look at this and you study this picture, you'll see that each of the formal charges of all of the atoms here are 0. There's another sign that this is a good Lewis structure and a stable one. And of course, all the phosphoruses here in this picture are in the +5 oxidation state, I believe. 20, yes. Okay, that's it for this video.